All right, let's look at an example. We saw about this example, x prime equals ax, and A was the matrix 1, 2, 3, 2. And we saw A has 2 eigenvalues. Two eigenvalues. R1 equals -1 with eigenvector C1 equals 1 and -1, and R2 equals 4 with eigenvectors C2 equals 2 and 3. So if you want to sketch the phase portrait, 1 and -1 would be here. So this is C2, and then C1. And sorry, this is C1, 1 and -1. And then C2, 2 and 3, so 2 and 3. C2. So C2 has a positive eigenvalue. So it gets farther and farther from origin. C1 has a negative eigenvalue. It's closer and closer to origin. And in between looks like this. Now, if let's say the initial location, if we start from here, let's say C1, then the phase portrait suggests that the particle will get closer and closer to origin. If you start from here, the particle will get closer and closer to origin as t goes to infinity. So we can say that according to figure above, if let's say x of 0 equals C1 equals 1 and -1, then as t goes to infinity, x of t will approach to 0, get closer and closer to 0. Now, this question wants us to verify this algebraically. So verify this algebraically by finding the solution of ODE or system of ODE above. System of ODE above. We have a system of ODE with the initial condition. We want to solve this and find x of t. Once we have x of t, we can find the limit as t goes to infinity. Our expectation is that as t goes to infinity, x of t will go to 0. Because this picture suggests that if we start from this point, then as t goes to infinity, we'll get closer and closer to origin. We want to verify this fact algebraically by solving the equation, this ODE, or this system of ODE. So what is the ODE again? The ODE is here. We already found the eigenvalues and eigenvectors in the previous examples. And we know that the general solution is a linear combination of like C1 e to power R1t and C2 e to power R2t. So we saw as seen before. So this is the answer. as seen before. The general solution can be written as, let's say, beta 1 C1 e to power R1t plus beta 2 C2 e to power R2t. So that will be beta 1 C1 is 1 and minus 1. So 1 and minus 1 e to power minus t plus beta 2 C2 is 2 and 3 e to power 4t. Now to find beta 1 and beta 2, use the initial condition. What was the initial condition? I was assuming that the particle starts from C1, x of 0 is C1, which is 1 and minus 1. So x of 0 equals 1 and minus 1. So this is my x of t, basically, right? X of t equals this, which is equal to this. So what will be x of 0? X of t is this. So x of 0, I need to replace t with 0. What do I get? So x of 0 equals beta 1, 1 and minus 1 plus beta 2, 2 and 3. And if this is equal to 1 and minus 1, then we can find beta 1 and beta 2. How do we find beta 1 and beta 2 in that case? So because x of 0 on one hand is beta 1 times 1 and minus 1 plus beta 2 times 2 and 3. And by assumption, x of 0 is 1 and minus 1. So then if we solve this, that gives me beta 1 plus 2 beta 2 equals 1. And minus beta 1 plus 3 beta 2 equals minus 1. So there are two equations with two unknowns. You can solve them. Or you can just guess, because see, look at this equation. Obviously, if I set beta 1 to be 1 and beta 2 to be 0, then left-hand side becomes 1 and minus 1, which I have, which is what I have in the right-hand side. So you can either guess a solution or solve this system, two equations with two unknowns. So after solving or by guessing, we can see that beta 1 has to be 1 and beta 2 has to be 0. So x of t will be beta 1 is 1, beta 2 is 0. So if I substitute back, x of t will be 1 and minus 1 e to power minus t, and beta 2 is 0. X of t will be 1 and minus 1 e to power minus t. And then once I have x of t, I can find the limit of x of t as t goes to infinity. Remember, the question was asking us to verify that limit of x of t as t goes to infinity is 0. The particle will get closer and closer to origin as t goes to infinity. So hence we can say that a limit x of t as t goes to infinity is equal to limit 1 and minus 1 times e to power minus t as t goes to infinity. And e to power minus infinity is 0, and 0 times anything is 0. So the answer will be 0 and 0. So if the initial location is at C1, The phase portrait suggests that the particle will get closer and closer to origin as t goes to infinity, and our calculation also verifies the same thing. All right, now let's move on to the next case where the matrix A, let's say, has two distinct complex eigenvalues. So next, if the matrix A has two distinct complex eigenvalues, two distinct complex eigenvalues. So suppose that A has two distinct eigenvalues, let's say lambda 1 and lambda 2 with the corresponding eigenvectors. It is C1 and C2. So first of all, note that lambda 2 should be lambda 1 bar, the complex conjugate of lambda 1. So if you have one of the eigenvalues, let's say one eigenvalue is 5 plus I is root minus 1. Let's say if one of them is 5 plus I, then the other one has to be 5 minus I. So how can we show this? Since if, let's say, A C1 equals, let's say, lambda 1 C1, if I take complex conjugate from both sides, then I'll have A C1 bar equals lambda 1 C1 bar. And then I'll get A, because I'm assuming A is real. So A bar will be same as A. So if a number is real, then if you take complex conjugate, you get the same number. Recall that, complex conjugate, you remember about the complex conjugate, right? So for example, recall that, let's say alpha plus I beta bar can be written as alpha minus I beta. So then A C1 bar, I can write it as lambda 1 bar, C1 bar. So that means A, so lambda 1 bar is also an eigenvalue for A with the eigenvector C1 bar. So in this case, if we have access to one of the eigenvalues and eigenvectors, then the other eigenvalue will be complex conjugate of the first eigenvalue, and the other eigenvector will be complex conjugate of first eigenvector with the eigenvalue C1 bar. Now suppose that we have access to one of the eigenvalues and one of the eigenvectors. If I consider lambda 1 times, C1 times e to power lambda 1 t. We have already seen before that if you have eigenvector and eigenvalue, let's say C1 and lambda 1, then C1 times e to the power lambda 1t is a solution for our ODE, for our system of ODEs. So X, I can call this one X1. So let's say X1 equals X1 of t equals C1 e to the power lambda 1t is a solution for our ODE X prime equals AX. Now, what will be the other solution? The other solution, the other linearly independent solution will be C1 bar times e to the power lambda 1 bar t, which is same as X1 of t bar. So if you have one of the solutions, then the other solution can be written this way, because we just saw 1 minute before that if C1 is an eigenvector, then C1 bar is also eigenvector corresponding to the eigenvalue lambda 1 bar. So this will be the other linearly independent solution, which can be also written as X1 of t bar. So what will be the general solution then? So general solution will be, let's say, some alpha 1 times X1 of t plus some alpha 2 times X2 of t, which is same as X of t, X1 of t bar. So now I want to make a claim that the general solution can be written this way. So if, let's say, X1 of t, remember X1 of t is a complex valued solution. I can write it this way. Let's say if I write X1 of t as u of t plus iv of t, let's say. If I write X1 of t this way, then the general solution can be written as, let's say, some constant times u of t. Let's say, for example, beta 1 u of t plus beta 2 v of t. So this means in order to find the general solution of our system of ODE in this case, we only need to write one of the linearly independent solutions, let's say X1 of t, which can be written as C1 times e to the power lambda 1t. Just write it this way. But here, remember, C1 and lambda 1 are complex valued numbers. And this is complex valued number. This is complex valued vector. So X1 of t will be a vector with complex valued elements. So I can write it as u of t plus iv of t. Here u of t and v of t are real valued vectors with u of t and v of t real valued vectors. Then I can write the general solution as some constant times u of t plus some constant times v of t. So in other words, the linear combination of u of t and v of t. So how can I prove this claim? So proof of the claim. So see, this is the general solution. I know that general solution is linear combination of linearly independent solutions, which are X1 of t and X1 of t bar in this case. So general solution, I can write it as alpha 1 X1 of t plus, let's say, some alpha 2 x1 of t bar. But I'm assuming that x1 of t is u of t plus iv of t. So I can write it as alpha 1 times u of t plus iv of t plus, let's say, some alpha 2 times x1 of t bar, complex conjugate of this vector, which is going to be u of t minus iv of t. In order to find the complex conjugate, you need to replace every I with minus I. And then I will have, if I simplify this, u of t times alpha 1 plus alpha 2. So alpha 1 plus alpha 2 times u of t. And then plus I times alpha 1 minus alpha 2. See, I alpha 1 minus I alpha 2. So I times alpha 1 minus alpha 2 v of t. Now, if I define this part as, let's say, beta 1 as alpha 1 plus alpha 2, and this part, let's say I can define it as beta 2, I times alpha 1 minus alpha 2, then this can be written as beta 1 u of t plus beta 2 v of t, which is what I claimed here. So the summary is to find the general solution. The general solution in this case, find lambda 1 and c1, then write x1 of t equals c1 e to power lambda 1 t in the form u of t plus iv of t, and then the general solution will be simply beta 1 u of t plus beta 2 v of t. So the recipe is simple. I only need to access to one of the eigenvalues and one of the eigenvectors, and then I construct x1 of t, write it this way. U of t and v of t are real valued vectors, and then the general solution is a linear combination of those vectors. All right, let's look at an example of this case. Example, find the general solution. General solution of x prime equals 3, 9 minus 4 minus 3 times x. So here we have a system of ODEs, and this is our matrix. So again, like always, the first step is to find the eigenvalues and eigenvectors of this matrix. First, find the eigenvalues, eigenvectors. Eigenvalues, eigenvectors. So here the matrix A is 3, 9, minus 4, minus 3. So I need to put or set determinant A minus lambda I equals 0 in order to find the eigenvalues. And I here is the identity matrix. Then this gives me determinant 3 minus lambda, 9 minus 4, minus 3 minus lambda equals 0. And now I can easily expand this determinant, this times this, minus this times this. So then I will have 3 minus lambda times minus 3 minus lambda. It's going to be minus this times this. So this is minus 36. Minus 36 becomes plus 36 equals 0. So that gives me lambda squared minus 9 plus 36 equals 0. That gives lambda squared plus 27 equals 0. So lambda squared will be equal to minus 27. And therefore lambda is equal to plus minus root minus 27, which is plus minus 3 root 3i. Root minus 1 can be written as I, and root 27 can be written as 3 root 3. So I can write the eigenvalues this way. So I have two eigenvalues, lambda 1 equals 3 root 3i, and lambda 2 equals minus 3 root 3i, which is, as I expected, same as lambda 1 bar. Remember, we just verified that if one of the eigenvalues is lambda 1 and it's a complex valued number, then the other one will be complex conjugate of that eigenvalue. So lambda 2 must be same as lambda 1 bar, which is the case here. And as we said, we have to focus only on one of them. Let's say we focus on lambda 1, and then we'll find the eigenvector corresponding to that. So eigenvector, the eigenvector corresponding to lambda 1. What do I need to do? I need to solve for ax equals lambda 1x. So let's say a times x1, x2. Or I can also write it as a minus lambda 1i times x equals 0. So a here was 3, 9 minus 4 minus 3. So 3 minus 3 root 3i, 9 minus 4 minus 3 minus 3 root 3i times x1, x2 equals 0. And then this will give me 3 minus, so x1 times 3 minus 3 root 3i plus 9x2 equals 0. And then also minus 4x1 plus minus 3 root 3i x2 equals 0. Now remember, we said that if this matrix is not invertible, which is the case here because this is how we found the eigenvalue. We found the eigenvalue in a way that this determinant of this matrix becomes 0. And therefore this matrix is not invertible. So in that case, we said that if you have a linear system in this form, then you have two equations, but one equation is the repetition of the other one, because once this matrix is not invertible, this system is going to have infinitely many solutions. And in order for that to happen, we need to have the second equation to be a repetition of the first one. For example, we said, a simple case of repetition of two equations, you can consider, let's say, x1 plus 2x2 equals 0, and 2x1 plus 4x2 equals 0. Well, in this case, it's obvious that the second equation is the repetition of the first one because you just need to multiply both sides by 2. But in this case, it's not obvious that the second equation is the repetition of the first one. But after some calculation, you can show that this is in fact repetition of the first one. Maybe I can leave that as an exercise here that so I can say exercise, check that the second equation, or this equation, let me say this equation is a repetition of the first equation above. So that means we can consider only one of the equations. It's enough to consider only one of the equations because the other one is the repetition of the first one. Although it doesn't look like it, it's not obvious, but after some calculation, it can be shown that it's a repetition of the first one. So let me consider the first equation here. So what do we have? We have 9x2 equals, let's consider the first equation. If I take this term to the other side, then I'll get 3 root 3 I minus 3 times x1. And then if I divide both sides by 9, then I'll get x2 equals root 3 I minus 1, the whole divided by 3 x1. So in order to find an eigenvector, remember we are going to have infinitely many eigenvectors, but we are only interested in the linearly independent ones. So I just need to set x1 to be, let's say, 1. So set x1 to be 1, and then I can find x2 easily using this equation. Once I know the value of x1, then x2 will be equal to root 3I minus 1 divided by 3. So the eigenvector will be, let's say eigenvector C1 corresponding to lambda 1 will be 1 and root 3I minus 1 divided by 3. So this is the eigenvector corresponding to lambda 1. So what will be the first equation then? Then x1 of t. We found the eigenvector. We also find the eigenvalue. Now we are ready to find the first linearly independent solution. x1 of t equals c1 e to power lambda 1 t. c1 is 1 and root 3I minus 1 divided by 3 times e to power lambda 1 t. And lambda 1 was 3 root 3I, so e to power 3 root 3 IT. Now we know that e to power I beta, e to power I beta can be written as cos beta plus I sine beta. Cos beta plus I sine beta. So I can write this one as 1 and root 3I minus 1 divided by 3 times cos 3 root 3t plus I sine 3 root 3t. Cos 3 root 3t plus I sine 3 root 3t. Now we need to write this in the form of u of t. See, this is my first solution, x1 of t. If I write it as in the form of u of t plus iv of t, then I can find the general solution. So write it, in the form u of t plus iv of t. So let's see how we can do that. So this is a 1 and root 3. So I can multiply. See, this is a number multiplied by a vector. So I need to multiply each element of the vector by this number. So 1 times this is going to be the same expression here. So cos 3 root 3t plus I sine 3 root 3t And then the other one, I need to multiply root 3i minus 1 divided by 3 times cos 3 root 3t plus I sine 3 root 3t. So I can write it as cos 3 root 3t plus I sine 3 root 3t. And now here I can expand it. So it's going to be the real value terms. So this term times this term is going to be real valued. This term times this term is going to be real valued. So 1/3 is a common factor. And then times minus 1 times this. So minus cos 3 root 3t. And then root 3i times I squared is minus 1. So minus root 3 sine 3 root 3t. And then this term times this term is going to be complex valued. So plus I times root 3 cos 3 root 3t. This term times this term is complex valued. This term minus 1 times this term is also complex valued. So minus I sine 3 root 3t. Now I want to separate it into u of t plus iv of t. So that means I want to separate the real part and separate the complex part. Now the real part in the first element, the real part is only this one. So I can write it as cos 3 root 3t. And then in the second coordinate, I have these two terms which are real. So 1/3 minus 1/3 cos 3 root 3t minus root 3/3 sine 3 root 3t. And then plus I times, now I want to write the complex valued parts. So this part is complex valued from the first element, and from the second element, these two terms are complex valued. And I've taken I as a common factor out already. So what will be left? I times for the first element, sine 3 root 3t. And for the second one, 1/3 times this and 1/3 times this. So root 3/3 cos 3 root 3t. And then minus 1/3 sine 3 root 3t minus 1/3 sine 3 root 3t. So this is basically my u of t, and this is my v of t. Once I find u of t and v of t, I can find the general solution. Write the general solution as some constant times u of t plus another constant times v of t. In other words, a linear combination of u of t and v of t. Therefore, the general solution of the system above can be written as follows. So general solution beta 1, let's say u of t, plus beta 2 v of t. So that's going to be equal to beta 1 u of t. It's this vector here, cos 3 root 3t, cos 3 root 3t, and minus 1 over 3 cos 3 root 3t, minus root 3 over 3 sine 3 root 3t, and then plus beta 2 times the other vector, which is sine 3 root 3t, and root 3 over 3 cos 3 root 3t, minus 1 over 3 sine 3 root 3t. This is the general solution of the system of ODE that we wrote above. Okay, guys, so we covered the case where we had two distinct complex values. We saw how to find the general solution. And next time we can look at also the phase portrait of this case, and we will also consider cover other cases that are still left. Okay, guys, so thank you and see you next time.